Congratulations, you built your first search system and you can finally answer questions like, show me all the dogs that are prancing outside in the snow. But wait a minute, a new user comes in and that user is asking a question that you had no preparation for. They're asking questions like, how many dogs have all four legs on the ground, there's snow outside, and Beethoven is playing in the background? Now, in order to support a new query like this, you need to actually reconfigure your index entirely. But the challenge is, indexes are actually very much stateful. They do not change, and it's really hard to migrate them. And so we introduced the concept of feature URIs in order to support the index lifecycle so that your indexes can evolve as your usage patterns evolve. So let's dive into it. What a feature URI is, it's four components. At the very front, we have the protocol. So that, in this case, is the MixPeak resource. We have the feature extractor. So we talk about feature extractors in a different video, but at its core, feature extractors are really just the ability to deconstruct raw files, videos, images, audio, documents into atomic units. Some of those atomic units can be metadata keys. Some of them can be embeddings. So we have the extractor, we have the version for the extractor, and then we have the embedding that is mapped to both the extractor and the inference endpoint, the managed model that encodes the inputs and the outputs. Now, all of these are important because they not only allow you to index data efficiently and version everything according to your lifecycle, but they also allow you to tightly couple the retrieval operations with the actual underlying index. So here are some examples of feature URIs in the MixPeak system. We've got different embedding models. We have different feature extractors. We have different versions, right? Face detector V2, face embedding. That might have a completely different combinations of models than face detector V1, face embedding. And you would only know if V1 outperforms V2 for your use case if you test them one by one. You migrate all your data, re-embed, re-extract, re-index, and then run retrieval across both of them and compare. Right, and so we already talked about why feature URIs are valuable. They enable you to version different embedding models where the embeddings are tightly coupled to the underlying data that is getting embedded. If you have a million videos and you want to test a new fine-tuned clip model, now you have to re-embed a million more points. What happens when the new fine-tuned clip model doesn't perform as well? Well, now you have to revert back to the previous 1 million points. And so feature URI versioning allows you to actually enable that lifecycle, that versioning, that rollback, all within a single API call. So that abstraction is really what the value is. And if you think about how embedding models are used, it's really much around finding data that is aligned to your access patterns. And when your access patterns evolve, your embedding models have to evolve, your indexes, etc. And so here is a bunch of examples. We have different extractors. Clip could be an extractor. Text embedding could be an extractor. Face detector could be an extractor. We have different versions. We have the feature URIs, etc. So enough about feature URIs. Let's dive into the actual product and see how it all comes together. And so this is a collection. I've already run files through the object decomposition. In this case, it is just a single collection. We're piping in the portrait gallery bucket into the gallery collection, and the gallery collection is just a single feature extractor. And that single feature extractor, let's take a look at it. That single collection is using this feature extractor, it's image extractor, and it has, as we can see, image extractor V1, Google SIGLIP base V1. So this is the name of the embedding field, this is the feature extractor, and this is the version. And so all together, that gives us both the version of the feature extractor, gives us the embedding field that we can do retrieval on, and it gives us the inference endpoint so that we don't have to think about the model or the hosting or the lifecycle of the model when we do our retrieval operations or our clustering. So let's take a look at the actual, let's build a retriever real quick, and we'll see how feature search is, how feature URIs are supported by feature search. So let's call this test, selecting the collection, and we'll just do a text query. So we have a bunch of documents in the collection, and we could see the stage that we're going to do is the feature search stage. And feature search has a ton of different parameters and ways of configuring it. So check out the documentation to see how it suits your access patterns. You can combine different feature searches together. You can do hybrid search. You can do learned, re-ranking, etc. And so in this case, we're just going to provide a test input. We'll say this is dog. And then what we're doing is we're providing dog, in this case, to the input value here. Since it's a Jinja tag, we can just inject the variable from the input schema of the retriever that we defined before. And then here, as we talked about, we have the feature URI, which is basically just mapping the underlying extractor, embedding model, version, vector configuration, index field, everything together in a single string. So let's run this. We can see we have our results. So each of these documents is just one result from the feature search retrieval operation. And we can see there probably is some kind of dog element to this, but since it ran a feature search on the image itself, oh yeah, so we see there's a keyword term theme dog here. But what we can do is, since this is the portrait gallery, doing this for a different demo, but we'll see the actual page here. So we can see that it does in fact have a dog in it, and it does. So the feature search did an embedding on, or ran a k-nearest neighbor operation on the image embeddings that were indexed before. And so we have 100,000 images that have already been indexed into this collection, and we're doing feature search using the feature URI. And so that's feature URIs in MakeSpeak. Not only do they allow you to do feature search, but what's really critical is they give you the ability to migrate from one feature extractor to another. So if you wanted to re-extract 1 million of those video points, test it against a previous, or test it against a new feature extractor. So let's say we have the image galleries that we just showed, and we want to use that as the source namespace. Well, now we actually select a new feature extractor, a new version, etc., and then it'll automatically re-extract everything from that previous collection into the new one, so that you have a way to A/B test namespace A with namespace B. And so then what you can effectively do is measure the performance of your results, not only the speed performance, but the precision and recall. You can draw evaluations between two different namespaces, which are tightly coupled to different extractors, different tokenization strategies, chunking strategies, and ultimately embedding models, which prior to this innovation were very tightly coupled and very hard to decouple because of how the embedding model is associated with the embedding, the underlying points, the retrieval operation, the inference endpoint, etc. And so that's what feature URIs are solving here. Thank you.